In our next section, we're going to talk about public key infrastructure and specifically how to implement it on iOS and ASA, and then how we can use this as an authentication mechanism for the IPsec VPNs. So first, we're going to talk about a general overview of how PKI works. We'll then look at configuring the iOS as a certificate authority server, the PKI server. We'll look at both the iOS and the ASA as PKI clients, and then ultimately how we can use this for the IPsec VPNs with a LAN-to-LAN configuration between these two platforms. Now, we will also come back a little bit later and talk about certificates and PKI as it relates to SSL VPN, and when we get to that point, we'll look at the ASA also as a PKI server. Now, PKI or public key infrastructure can be either a flat or a hierarchical system. And the way that the PKI system works is that there's going to be always what is considered a root CA or a root certificate authority. This is essentially just going to be the server that is the primary top of the tree, essentially, or in other words, just the first certificate authority that is installed. So the root CA is going to generate its own certificate, which is what we call a self-signed certificate. And then it is going to be issuing certificates either to end clients or other certificate authorities that are below it in the hierarchy, which are called the sub-CAs or the subordinate CAs. Now, the subordinate CAs are basically used in order to add some redundancy to the CA system and to make it a little bit more scalable, so we don't have every particular device in the network enrolling with one individual server, the root. So then if the root were to go down, we would have some issues with recovering all those certificates. So in larger scale designs, you typically have the root CA and then the subordinates, which are going to have potentially multiple levels of hierarchy. So the subordinate CA is then going to get a certificate issued by the root, or potentially some subordinate CA that is higher than it in the hierarchy, and then it's going to be issuing certificates to a lower level certificate authority, a sub-CA, or to the end clients. So both the root CA and the subordinate CA can issue certificates downwards, but not upwards. So the root of the CA is essentially going to be the top of the tree. The subordinate ones are going to be downstream of that, and then they can all issue certificates downstream. Now, the third role in the hierarchy is known as the registration authority, or the RA. This is technically not a CA server, but is more of a proxy to receive requests from the clients and then forward them upstream to the either the root certificate authority or to the subordinate authorities. So again, the idea with this hierarchy is that we're adding more scalability to it and more redundancy to it, where the registration authority might be the only portion where your end clients can talk to, so they don't have reachability directly to the subordinate CAs or the root CAs. So the registration authority, this is going to be what is authenticating and then authorizing the client requests. It's going to forward them upstream up the tree, but it's not going to be generating its own certificates. So in other words, it asks someone else above it, can I generate or can you generate a certificate for this individual client? Send it to me, and then I will forward it on to the final destination. Now, what the certificate authority is being used to do is to generate what we call a digital signature, or in other words, the certificate. Specifically, the certificates are called X.509 certificates. That's talking about the specific format of the actual file. And basically what it's used to do is just to uniquely identify either an end user or a device. So when you go to HTTPS, google.com, Google is going to return an SSL certificate, an X509 certificate, saying, I'm google.com, I'm not some other third party that's trying to fake being that website. Now, specifically inside of the certificate, there's a bunch of data in here that's going to be used to validate the information against the certificate authority. So it's going to include the serial number of the device that's requesting it and also the version. It's also going to include the issuer's identity, which is going to be the common name. We'll see this when we look at the specific enrollment and the configuration on the iOS and the ASA. Then also the the identity of the device that was requesting the certificate. So it's talking about the issuer's identity, that's the certificate authority, and then the device that requested it would be like the VPN client's name, or it could be your router's host name that is the PKI client. Now, the other two real important pieces of information in the certificate are going to be the device's public key and then the CA's signature. Now, we'll talk about a little bit later in more specific details how these are used in order to do the authentication and to make sure that the certificate is valid from a trusted certificate authority. And then last but not least, we have the validity period, which is just going to be a time interval where you say starting at interval X and ending at interval Y, this is going to be some sort of valid period. Now, the reason specifically that we're talking about this here, PKI and the digital signatures, is that we're going to use these certificates for the Phase 1 negotiation for IKE version 1 and IKE version 2 for IPsec VPNs, and then also for our SSL VPN authentication. Now, in order to get the certificates are going to be issued by what we consider to be a trusted third party. So in the normal public PKI design, like for SSL websites, trusted authority would be like VeriSign or GoDaddy, some sort of central CA that your web browser already trusts, so that when you receive a certificate from a website, if you go to https www.ine.com and it returns the SSL certificate to you, and it says this was signed by VeriSign, if your browser already has VeriSign's public key, basically the certificate authority's public key, you can check it against that and then figure out, yes, this actually is ine.com. It's not some other website that is trying to spoof it. But the key point about the public key infrastructure, in order for this to work, we have to have that trusted third party. That I say, you trust the CA, I also trust the CA, we'll exchange our certificates together. If the CA says that those are valid, then we can assume that each other's identity is also valid. So this is different than other types of authentication like MD5 or SHA, where we're just looking at, I present you a hash, you do some sort of operation and come up with your own hash. If they match, then yes, we're authenticated. So the whole point of this is that we have to have the third party in there, which is the certificate authority. Now, the actual process of getting the certificate from the CA is what we call the enrollment process. Now, CA enrollment can be either automatic or manual. Manual being you could go to VeriSign's website, paste in your public key, they sign it, and then return you a text file that you paste into the router, or you double-click on your Windows machine and then it installs the certificate. Auto-enrollment, as we'll see, is going to be based on a couple different mechanisms. The one that we're using is going to be called the Simple Certificate Enrollment Protocol, or SCEP. Now, the process of doing this enrollment end-to-end is first going to start with the client generating both a public and a private key pair. So this public-private key, this would be similar to what you would use for your SSH sessions, where, of course, the private key is the one that you have to keep secret, and then the public key is the one that you can distribute out to the other devices. But the overall logic of PKI is that it is an asymmetrical encryption and decryption, that if you encrypt something with the private key, you can decrypt it with the public key. And likewise, if you encrypt something with the public key, you can decrypt it with the private key. So that's always going to be the first step, is that we need to generate this public and private key pair. Next step is that we're going to send the certificate signing request, or the CSR, to the certificate authority server. Now, the CA server could be anywhere in the hierarchy. It could be the actual root CA, could be a subordinate CA, or it could be just a registration authority, an RA, that's going to proxy the request up to some other device higher in the CA's hierarchy. But regardless, the end client is going to send that certificate signing request, and in this request, the client is going to include their own public key. So of the public-private key pair, we're sending the public key to the CA. We're also going to include some additional attributes, like the common name is going to be like r1.ine.com, asa1.ine.com, and then also this is going to be in a well-known format that is called PKCS number 10. Now, once we send that certificate signing request, the certificate authority is going to sign our public key with their private key. Because remember, you can take your own private key and sign something that can then be decrypted with your public key. Or vice versa, you can take your public key and sign something that can be decrypted with your private key. So the certificate authority is signing the client's public key. The end result of this is the actual certificate. Okay, the client is going to receive back not only its own signed public key, which is their certificate, but it's also going to receive the certificate authority's public key. This is the CA's certificate, and this is the one that we're marking as trusted. So this very last portion is why we need that third party in the PKI design, that if everyone is trusting the same CA's public key, we can use that to compare against our own certificate and other people's certificates. And if we end up in the same hashing result once we go through the actual mathematical calculation of it, then we can compare the two results. If they're the same, then we know that we both had certificates that were signed by the same trusted CA or by the same trusted CA's hierarchy. Now, as I mentioned, there's a couple different ways that we can obtain the certificate. One of them that we're going to be looking at is with the automatic enrollment using SCEP, or the Simple Certificate Enrollment Protocol. So this is the one that works over regular HTTP, which implies that we need to make sure that TCP port 80 transport is available in the network. So if we look at our particular topology here, we're going to be using on router 2, this is going to be our CA server. So if router 2 was on the inside of the ASA, and we have, let's say, a client request that comes from router 3 on the outside, then we need to make sure that we have TCP/80 reachability from the client to the server. So this isn't necessarily specific to the PKI infrastructure. It's just assuming that we have underlying transport there, that nothing is being filtered out for the automatic enrollment request. Okay, this also means that on whatever device that we're running, the CA server that is running SCEP, we need to turn the HTTP service on, where in our case, this is going to be the iOS router. There's also another way that we can use with Windows Active Directory, which is called ADCS, Active Directory Certificate Services. But of course, that's going to imply that you have your AD servers that are part of the CA's hierarchy. Now, another big consideration we'll see here is that the certificate has a valid lifetime, which again is going to be some sort of finite starting period and some sort of finite ending period for the certificate, which means that we need to make sure that the client and the server have synchronized clocks. And the way that normally we're going to do that is with the network time protocol with NTP. So before we configure the CA, the root CA, and before we configure any of the clients to generate the requests, we want to make sure that generally that they are synchronized to the same NTP infrastructure. Okay, the other way we could do this is with a manual certificate enrollment. This would be like when you web browse to GoDaddy's certificate enrollment page, you paste your own public key, and they return back to you your certificate, and then you would basically go to the router and paste that in the CLI, or take the file and double-click it on Windows or Mac OS, and then it enrolls that as your own local certificate. Now, for the server, in this example, for this section, we're going to be dealing with the iOS router as the CA server. As I mentioned, you can also have the ASA be a CA server. It doesn't have the same feature parity as the iOS does, so we're going to be looking at that specifically within the scope of SSL VPN, and then how we can get our Windows hosts with the AnyConnect client to enroll with the ASA CA server. But with the iOS CA server, it's essentially fully functional, which means that it supports hierarchy and the different roles. So you could have one router be the root CA, you could have other routers be subordinate CAs, and you could have other routers lower down the chain be the registration authorities. It also supports high availability in an active and standby mode. So the idea of this is that if you have your root CA and it goes down, and we were holding all of the certificates locally, then it means that we won't be able to do any new certificate granting requests. So it does have active standby, where basically you can synchronize the CA request between two routers running HSRP. Does support auto-enrollment versus SCEP. We'll see that we can do the SCEP client enrollment with the iOS PKI client and the ASA's PKI client. So you don't necessarily have to generate the certificate request and then paste it into the CLI to get the result back. We could also do manual enrollment if we wanted to, so you can copy and paste their certificates into the router. The other thing it offers is what's known as the Certificate Revocation List, or the CRL. And the CRL is used that if one of your devices gets compromised, then you can tell the PKI server that I want to invalidate the certificate or to revoke it. And then periodically you can have your clients request this certificate revocation list, and that's going to say these are the certificates that are no longer valid. So let's say, for example, you have a user that has a laptop with the AnyConnect VPN client on it, and they're using a certificate that was enrolled to the router. But then they lose their laptop or somebody steals it, and you want to make sure that they cannot log onto the VPN. So what you would do is go to the CRL, revoke their certificate, and then the other devices would be checking that revocation list to say, is it actually valid to be used as a certificate? And then, of course, if the cert is in the CRL, it means that it's not valid. It has been revoked, and you cannot authenticate to it. Also, NTP synchronization is going to be required for the CA server. In general, when you're using PKI, you always want to run NTP. There's not any reason not to do that, because the issue becomes here that if you get towards the end of the validity range of the certificate, and let's say your clock is an hour off or your clock is a couple days off for some reason, then like your VPN server, let's say the ASA's clock is off, then it could start rejecting the VPN clients from connecting if it thinks their certificates are not valid. So you always want to make sure that you're running NTP when you're doing this on the different devices. Now, from a configuration point of view, in iOS, this is going to be configured under the Crypto PKI server mode. Now, we'll see that there's a lot of different functionality that we can do here with the iOS CA, but for a minimal configuration, it's a very straightforward config. It's only a couple lines where we turn the PKI server on, tell it to generate its own CA's signing certificate, which is going to be the private key. Then we can also add other options on there, like do we want to do the revocation list? Do we want to do high availability? What is going to be the valid lifetime for the certs that we are granting? We could also say, do we want to automatically allow certificates to be granted so we can do auto enrollment, or are we requiring the clients to do manual enrollment? So out of this, we'll see once we get to the CLI here shortly. The config is pretty straightforward. You basically turn the PKI server on. You can say what is its mode. Is it a sub-certificate server, which is going to be not the root server, but is going to be a subordinate CA, or is it a registration authority? So is it basically just a proxy that is supposed to go upstream towards the other servers? So once we have the PKI server on, we have to say no shutdown. That's going to enable it. And then assuming that we are doing SCEP for automatic enrollment, we need to turn the web service on, so the HTTP server, and then also we want to run NTP synchronization. So technically, it doesn't necessarily need to be the NTP server, but it just has to be an NTP client at least. Now, the verification for this is going to be under Show Crypto PKI. So we'll see when we do this configuration. The big thing that you want to look for here when you're looking at the PKI server is that it's actually running. So if you forget to say no shutdown, or if you forgot to enable the web service, then it's not actually going to be able to grant any certificates. So you might have two nearly identical configs and it looks like it's going to work, but then you try to enroll and then the CA server is going to reject the requests. So once the config is done, this is mainly just the one thing we need to look at, which is going to be the Show Crypto PKI server. We can also look at what are the outstanding requests, what are the certificates that we actually granted, and if we have a certificate revocation list, we can see which ones are in the CRL. Okay, normally you're only going to see the requests here if you are waiting to manually grant them. If you're doing auto-enrollment, then as soon as the request comes in, the CA server should automatically go ahead and allow that. It should issue it. Okay, if you want to do manual enrollment, you can say that you want to grant the certificate. You can also revoke someone's certificate here, and then you could also remove or reject it based on the identifier. So again, you normally don't need to do this though unless you're doing manual enrollment or you want to revoke someone's certificate to put it in the CRL. The two debugs that we're going to look at here are going to be debug crypto PKI server. That's on the server. On the client, it's going to be debug crypto PKI transactions. Okay, so again, in our particular topology here, we're going to be using router 2 as the CA server. So let's look at this configuration first, which is going to be to configure router 2 as the server and to get it to generate the public and private key pair that is going to be for CA signing. So first, let's go to router 2. And there's a couple things that we want to check before we actually get into the PKI config. Okay, one of them is going to be, do we have a domain name configured? So if we show run include domain, we can see right now the domain name is INE.com. This is going to be needed along with our host name to generate a fully qualified domain name, which is a requirement of the public-private key pair. So it's the same as when you're enabling SSH. SSH is going to use the general purpose keys, and you cannot generate those keys unless you have a fully qualified domain name. So we're assuming that's a step that we already did here, that we specify IP domain name, abc.com, whatever it is. Okay, next we want to make sure that the time is synchronized. So if we look at the show NTP status, we have router 2 already synchronized. We can see it's synchronized with router 1 as the server. It doesn't really matter what the stratum here or how accurate the clock is. As long as the routers are pretty close within their time, then it's going to be fine. Okay, also if we look at the show round pipe include HTTP, we can see the HTTP server is off, which is normally going to be the default on the router for security reasons. So if we're going to do, if we're going to enable the SCEP server, then we also need to turn HTTP on. Okay, so let's go to global config, and now we're going to turn the PKI server on. So crypto PKI server, we give it any name, let's say root CA. And from here, you'll see that there's a bunch of different options that you can configure, like where is the certificate revocation list? Where do I store the database? So do I want to store it in Flash or do I want to store it on some remote server? So for high availability, you probably wouldn't want to keep this locally on the router's Flash. How are we going to grant the certificates? Are we going to grant them manually or auto? Or we could say basically just turn off SCEP completely. This would mean you have to do manual enrollment. In our case, we're going to do auto enrollment. So let's just say anybody who sends a request, go ahead and grant it. Okay, we could specify what is the, let's say the lifetime for the let's say the client certificate. So when I issue a certificate to the client, how long is it going to be good for? So let's say 1 year, 365 days. Okay, most of the time you'll see the certificates are probably around 2 years or so, give or take. But it's, you know, any arbitrary configurable value there. The other thing that we want to put here is what is the issuer's name. So this is going to be inside the certificate that we grant to the clients. In our case here, let's say that the common name is going to be just our fully qualified domain name. So r2.ine.com. Now this does have that well-known distinguished name format where you can say things like the organizational unit, the country, etc. But technically you don't have to configure the whole thing. From here, pretty much that's it, which would be the minimum configuration. So you could say like what is the hashing that we're going to use. You can change what the algorithm is, and of course, you know, SHA 512-bit is going to be more secure than SHA 1. But the only other thing we need to do as a minimum is basically just to say no shutdown. Okay, it says some server settings cannot be changed after the CA certificate is generated. Please type a passphrase to protect the private key. So this is going to be any arbitrary password. And we can see now the router is generating its certificate authority signing certificate. So if we now look at the show crypto PKI certificates, we should see that we have the CA certificate, that's the root certificate, and the usage of this is going to be for signing only. So this is different than a general purpose key that you could use for SSH, or if the router is running the SSL VPN service as the server, those are going to be separate certificates that you would use. So if we wanted to generate, if we wanted a general purpose key, we could also have the router locally enroll with itself, because this public-private key pair here is just going to be used for granting other certificates. It's just going to be for signature here. Okay, if we then look at the, again, show crypto PKI server, this is going to be our main verification, show crypto PKI server. And it says right now the server is disabled, and the reason why is that the web service is off. So again, you do need to make sure, assuming that you're doing SEP enrollment, that we say IP HTTP server. Otherwise, it can't actually grant the enrollment requests. So we can see from the log message now, it says the PKI server is now enabled. If we show crypto PKI server, okay, now the status is actually on. Okay, it says database level is minimum, no cert data written to storage. Normally, you would not want to do this. This means that when you grant a certificate to someone, you basically, throw it away. You're not keeping a copy of it. In most real designs, you would have some sort of external database on a server that you would want to maintain these certificates on. Okay, so our next step then would be to enroll the clients. Now, from one of our previous examples with LAN-to-LAN VPNs, we had a VPN that was going between router 1 and ASA 3. And router 1 was trying to get traffic from 150.1.1.1, its loopback, to this VLAN 27 segment over to switch 2. And for our phase 1 policy for IKE v1, we were using pre-shared keys. Now, once we're done with the PKI enrollment, so router 1 is going to enroll with router 2, and ASA 3 is going to enroll with router 2, we could then change our ISACAMP policy to say instead of using pre-shared keys, we're going to use RSA signatures. And assuming that both of the peers of the VPN tunnel, so router 1 and ASA 3 in this case, assuming that both of them trust the same certificate authority server, and then they will be able to use each other's certificates in order to authenticate the ISACAMP sessions. Okay, so next step is we need to get the router to enroll. So first step for this is going to be to tell the router who is the certificate authority server, or what they call the trust point. So we say crypto PKI trust point, give it some arbitrary name, and then say what's the address that we're going to enroll with. Okay, in this case, this is going to be the address that's located on router 2. So on router 1, we're going to say crypto PKI trust point, and we'll say that the trust point is going to be router 2. And the enrollment URL is going to be router 2's loopback. And we're doing this through HTTP because, again, we have the automatic enrollment for SEP, the Simple Certificate Enrollment Protocol, enabled on the server. So we just basically web browse to router 2, and then router 2 should grant the certificate back to us. Okay, the next thing we need to do is to generate the public-private key pair on router 1, because router 1 is going to have its own private key that stays secret. It's going to have its public key that it sends to the CA server. CA server signs it with its private key, sends it back. The end result of that is going to be the certificate. So next we need to configure router 1 to generate that public-private key pair. Now this one here, when we say crypto key generate, Crypto key generate RSA, and then these are going to be our general purpose keys. Okay, then we say how long do we want the key to be. We could also say a specific label, like if we said that this is our IPsec PKI, and then what is the key length? So what's the modulus? Okay, so let's say like 1024. Okay, now if we look at the show crypto keys, my public key, RSA. This shows our general purpose key, which is going to be the, which one is the public one? Should be this one. This is the public key. Okay, next step is that we need to actually enroll with the device. So if we look at the show run section PKI, we have the trust point, so we know that router 2 is going to be listening at 151.22 at port 80. This says when we do the enrollment, we want to, and this is the default here, this says to check the certificate revocation list. Now in this case, since I didn't configure the CRL on the CA server, which again, that's the list that says these certificates are no longer valid, we want to tell the client that it doesn't need to check that. Otherwise, it's not going to be able to actually use this for authentication. So under the crypto PKI trust point is router 2. We need to say that the revocation check is none. So just ignore that for right now. Okay, but in a real design, you would want to use the CRL because that's how you invalidate somebody else's certificate. Okay, next thing we need to do is to, or actually one thing I skipped here was under the trust point, I need to tell them to use this particular key that I generated, which was the IPsec PKI. You technically don't need to do this, but the reason that you have the label is you might have multiple CA servers, so multiple trust points, and you can theoretically use different public-private key pairs with each of them if you wanted to. So you can have multiple keys and then say for CA1, use key 1, for CA2, use key 2. In our case, we only have one CA and only one key, but since I gave it a name, we're going to list it here anyways. We're going to say that our RSA key pair and then whatever the name is. So the name was here IPsec PKI. Okay, now on the server, which is router 2, we're going to look at the debug crypto PKI server. And let's make sure we're logging to the console. On the client, which is router 1, we're going to, let's log to the console, debug crypto PKI transactions. Okay, next step is we need to get the CA's public key. Because again, when we receive someone else's certificate, we're going to take the CA's public key, combine those two together, the end result is going to be a hash. That hash is how we figure out that we're trusting the same certificate authority, and it was actually signed by someone that we are trusting. So we need their public key, the CA's key to begin with. And the way we get this is by saying crypto PKI to authenticate, and then whatever the server's name was. In our case, we called it router 2. So we can see from this debug, this is the PKI transactions. You can see essentially they're sending HTTP messages. They're requesting the cert, and then the end result is that it's replying back with it. You can see here it says, this is the certificate. Do I want to accept it? Yes, I do. And it says their certificate is valid from January 29, 2014 through January 28th, 2017. If we look at router 2, we should have seen that we received the SCEP request and we gave them our certificate. Okay, next is we need to actually get our certificate. So we need to enroll with them. So we said crypto PKI authenticate. Now we need to say crypto PKI to enroll. Okay, this password here is anything arbitrary. It doesn't have to match what you configured on the CA server. Do you want to include the router serial number in the subject name? Sure, you don't necessarily have to. Do you want to include the IP address? Sure. Enter the interface name or IP address, let's say our loopback. Request the certificate, yes. So now we should see the SCEP request. You can see that it's a web request. If we look at router 2, we should see that we got the enrollment request. And it says that the request has been authorized. The reason this is the case is because we're doing auto enrollment. It says that we are now going to generate the certificate and send it back to the requester. So this is successful. Really the only time that this would be denied could be maybe if the time is different between the client and the server, or if you have the server configured to reject the SCEP enrollment. So if you're trying to do only manual enrollment, then it would not grant this. Okay, if we look at router 1 now and look at, or I think it asks a question. I think it says, do you want to accept this? Request the certificate, yes. And then the end result should be certificate is granted. So without the debug on, this is the normal result that you're going to get. This is just a normal syslog message, which is this one here. Certificate received from the certificate authority. So if we now look at the show crypto PKI certificates, we should see two different things. We should see the CA's public key, which is the CA certificate, and then we should see our own certificate. So this one we can see this is us. This is r1.ine.com. It was issued by the CA server r2.ine.com. And then inside here, this is our specific information that goes inside the like the distinguished name. Okay, the CA itself is r2.ine.com. Okay, so again, the first thing that is before this, it's not listed on the slide, is that you need to generate the public-private key pair on the client. So we're assuming the client has the private key and the public key. It's going to send the public key to the CA. That is part of the enrollment request. So we authenticate them. That's getting their certificate, and then enrolling is asking them to give us a certificate back. Now, if we were doing this on the VPN client, like in Windows, we would specify the address of the CA server and then add this well-known string after it. So it's under cgi-bin/PKI client.exe. And then the VPN client software should be able to get the enrollment request granted back to them. Now, in the case of the ASA is going to be pretty similar, where it supports both the PKI server and the PKI client. We'll see later in SSL VPN, we're going to talk about the server functionality because it works a little bit differently than the regular router does. Now, to do the enrollment, this is going to be pretty close to the router. So we're assuming that we have our public-private key pair to begin with. We're going to configure the trust point. So configure or give it any arbitrary name, and then we're going to say what's the enrollment URL. Then we're going to authenticate them, which is getting the CA certificate, so crypto CA authenticate, and then we're actually going to do the enrollment, which is to send the certificate signing request. That's crypto CA enroll. So pretty close to the same as we have in iOS. Okay, so on the ASA here, if we look at the show crypto PKI or show crypto key, my public key. My public key RSA. I believe the ASA is actually going to generate this automatically when we go to do the request. So after we do the request, let's come back and look at this here, and we should see that it has its own key. Okay, so in global, we're going to say crypto CA trust point is, we'll say router 2. We need to specify here the enrollment URL. So how do we, or where do we send the SEP request to? So the enrollment URL is going to be router 2's address, 150.122. Just like in iOS, we would need to say, do we want to do the revocation check against the certificate revocation list? Again, the default of this is on, so if the CA server doesn't give you the CRL, then you're not going to actually have a functional configuration. So again, normally you would want to use the CRL, but for the case of brevity here, we're just going to ignore this. So the revocation check here is none. Okay, now we need to authenticate the CA. So crypto CA authenticate router 2. Do I accept the certificate? Yes. If we now look at the show crypto, I think it's Ike v1. No, show crypto CA certificates. So this is router 2's public key, the one that we're going to use to compare against someone else's signature. And if we look at the show clock, we can see that our time is within the valid range. So it's 11:42 now. Theirs started at 11:25. So we just need to make sure that our clock is somewhere within that range. Okay, then we need to enroll with them. So crypto CA enroll with router 2. Signature public key not found. So I think what happened here with the default initial config for this ASA that it deleted its cert. Normally it normally automatically has one when you start up. So let's go ahead and generate a new one. Crypto key generate RSA. These are, we'll say, general keys. And the modulus, what size? Let's say 1024. Okay, if we now show crypto key, my public key, RSA. Okay, now we have a key pair. So again, you can't actually do the certificate enrollment unless you have the public-private key pair to begin with, because you have to send the public key to the CA in order to get signed. Signing result is the certificate. So let's try again to enroll with them. Again, this is any arbitrary password. Do we want to include the serial number, or the, serial number, sure. Request a certificate, yes. Certificate has been granted. Okay, so again, this is the final result that we're looking for here. If you didn't see this, again, normally the common problem of this is going to be the time. So if they're not NTP synchronized, if the CA server is ahead of the client, then the request is going to get rejected. The other reason why would be if you're doing manual enrollment, then you have to basically paste the request to the CA server, grab that certificate result, and then paste it back into the client. So if we now look at the show crypto CA certificates, we should see that we have two things. So we have the CA's certificate, again, which is router 2, and then we have our own certificate that is us, asa3.ini.com.